Hi everyone, welcome to this new QuTech360 seminar. Today I have the pleasure to present Guanzhong Wang and Tom Dvir. Our first speaker is Guanzhong Wang. So Guan received his master's degree in applied physics from TU Delft in 2017. And since then, he has been a PhD student in the group of Leo Kouwenhoven at QuTech, working on electron transport in hybrid semiconducting and superconducting nanowires. Guan will present a talk on singlet versus triplet Cooper pair splitting in indium antimonide nanowires. So the floor is yours, Guan.
Thanks, Gracia. Just make sure you can still hear me. Yeah, okay. So good afternoon, everyone. Thanks for coming to the talk. And I will take roughly half an hour to introduce you through roughly two ideas that we can explore with this one quantum dot superconductor quantum dot device. But before I go into the main topic, I want to thank our collaborators that did this project together with Tom, Greg, Nick, Boss, Alberto, Leo, among many others. And also thanks to Growth from Eindhoven. And there's a lot of important theory done by Trinshao and also Michal here at Curie. So I also am compelled to show this to you and remind you that because this is still an internal discussion within QuTech, we have to present this, send the video through Microsoft before we can disclose it to the public. So please treat this as internal discussion for now. So without much ado, I've jump in and let's see this device that I will be talking about for the next half an hour, also Tom in the next talk. What we have is a Kubernetes pair splitter device. Plainly speaking, this is a narrow strip of superconductor housing a sea of Kubernetes pairs, sandwiched by two quantum dots, one on each side of the device. And what we can use this device for is actually, there are a lot of possible potentials. For example, I can list three, widely speaking, goals. The first one is perhaps of more relevance to a lot of you at QuTech, namely electron entangler. And the reasoning behind it is basically that all the Cooper pairs inside a superconductor are already paired up in an entangled state, namely the Bell state in spin space. So suppose we can extract this resource of entanglement. We can separate the two electrons into these two separate dots and do manipulations on them afterwards. This would be a very easy way of generating entanglement. The second angle is a lot more relevant for people, for example, working with unconventional superconductivity. And the idea is that we can also use our quantum dots as a very effective detector of the spin, among other things. And for example, suppose we have found a very unconventional piece of triplet superconductor. And this is very rarely found in nature, but however, we can engineer it in the lab. Suppose we have Cooper pairs made up of a rather unconventional up-up spin pairing. And we would be able to, at least we speculate, we should be able to see that our quantum dots would only show up as accepting Cooper pairs being split when they're also both up. Of course, the third use, which we'll also expand on a lot in the next talk, is to use this thing as an exotic state generator. For example, without spoiling too much of the next talk, I would just briefly say that we can also regard the quantum dots as the interesting objects over here in this device. So instead of having our attention focused on the superconductor, we can look at the quantum dots and count how many electrons are on it. On the left, for example, we have either 0 or 1. On the right, we can also have 0 or 1. And the superconductor really allows us to create this new type of state, namely a superposition between 0, 0 and 1, 1, which you do not really get without the superconductor in the middle. So in my talk, I will be focusing mostly on the first two goals, and especially the second one, using the quantum dots to detect the spin texture of the superconductor, while briefly also mentioning the first one. So here's an overview of this idea of unconventional superconducting spin pairing, how we generate it in general, and how people have discovered, have detected in the past. So in general, the spin triplet superconducting pairing can be generated by two ways, starting from a singlet superconductor, because as we know, these are the most common superconductors in the world. aluminum, lead, tin, as you name it, they're all singlet, they're all S-wave. But starting from there, we can first of all, one way of doing it is to add a whole bunch of different micromagnets polarized along different axes. And this inhomogeneous magnetic field generated by these micromagnets can compel the spin to take on a different pairing flavor. For example, then you can have equal spin pairing. And the second way of doing it is to let go of this inhomogeneous field, because in practice, this is rather hard to engineer. What we can also do is to instead use a spin orbit coupled material and then apply a uniform magnetic field. If we have these two ingredients, we're also guaranteed to have, we're also expecting to have a spin triplet pairing. And have people managed to really detect the signatures arising out of equal spin Cooper pairs? The answer is actually yes. However, with the caveat that most of the experiments done in the past have really only focused on detecting the macroscopic properties of equal spin Cooper pairs. What I mean is that, for example, we expect an up-up Cooper pair, a triplet pair, to be a lot more resilient to magnetic field than a normal S-wave up-down minus down-up. And then we can detect the supercurrent in Josephson junctions, or we can study the superfluid density. We can study their macroscopic properties. But however, here in our experiment, what we want to do is something different. And what we want to do is, of course, using dots, measuring things on a single electron level. We take one Cooper pair, and we ask if we split this one Cooper pair into 2 electrons, can we still use the dots to diagnose the spin inside this engineered unconventional superconductor? So to do that, we need a superconductor in the middle, and then we need 2 normal metal leads on the 2 sides because they can have single electrons. And our first challenge is to make sure that our 2 electrons do not do this so-called end-drift tunneling and tunnel as a pair together into one side, because we still want to separate them first. And the method people have found in the past is to insert a quantum dot into each of these normal superjunctions. And then, because the quantum dot carries very strong Coulomb repulsion, it really does not like 2 electrons occupying one dot. So in this way, we compel the 2 electrons to be separated into 2 different sides. This, of course, doesn't solve one other problem, namely, we can still have the 2 quantum dots exchanging electrons among each other. So this is called elastic co-tunneling. And this co-tunneling process is really going to happen no matter if you have a Coulomb repulsion or not, because it's still a 1 electron process. There's no pair tunneling required. So before I look at our experiments, I'd also want to remind you of what has happened in the past with Cooper splitters, because people have been trying to make these devices for a decade. And what do we have now? And this is actually this is really the best Cooper splitter signal I can find in the literature. And what you see is in this measurement, you have 2-dimensional sweeps. You have the left dot energy and the right dot energy as the 2 axes. And in these 2 plots, you see the left dot current, left dot conductance, and the right dot conductance. One amazing, very important feature is basically you see these lines instead of dots, which means that this is a feature that only responds to one of the gates, either on the left or on the right. And what is carrying the current over here does not really depend on the non-local gate. And that means it's a local end-drift tunneling process. So although we really do want to use charging energy to roll out these local processes, they're still prevalent in previous studies. And in fact, if you look at this top measurement, they contribute to majority of the signal. Really, most of the signal comes from local tunneling. And the second problem that people have always struggled with is that, imagine if you have a ideal Cooper splitter, you only have pairs tunneling to both left and right at the same time. You should really expect your left and right conductance or current to be exactly the same. And this is really not what happens. Because on the right side, even if, for example, we see over here where there is a very strong point-like feature, namely the current really becomes strongly resonant when both dots are at Coulomb charge degeneracy. However, the 2 conductances on the 2 sides of the device are nowhere near equal. So why did people struggle with all these problems? Our understanding now is that basically the dots they use were not good enough. They're not pure single electron eigenstates. And to show you the idea of why making the dot better will make a difference, we can first take a look at the charge degree of freedom of the quantum dots. And by this, I mean that if you place a quantum dot above the Fermi energy, its excitation is rather electron-like. And if you place it below, its excitation is hole-like. So now we can imagine that we can also understand this Kuiper splitting process as the so-called crossed and derivative reflection. Namely, we can shoot an electron from the left side into the superconductor. It can be transmitted, come out as a hole on the right side. So if we, in fact, anti-polarize the charge in these two junctions, one preferring electron, one preferring hole, we can strongly facilitate Kuiper splitting. And of course, our quantum dots, as the spin qubit groups know very well, they also have very nice spin eigenstates. So we can also use the spin degree for freedom, and this will be what I will focus on a lot in the upcoming slides. But before that, let's first take a look at the device. What we have is an indium antimonide nanowire in this green in this SEM image, and we have two normal leads made of gold, and then a middle superconducting lead made of aluminum with a fine sprinkle of platinum on top. And using these red bottom gates, we define one quantum dot in each of the nanowire junctions. And finally, we plug it into the circuit where we ground the central aluminum lead at all times throughout this experiment. And we can apply voltages onto these normal leads separately. And we can also measure the currents flowing through these two normal leads independently. And so, finally,
can I ask you take questions during the talk or before at the end?
Either way for me. You can just ask now.
Well, I'm just if you go back to the measurement from what was it 2009 or so, yeah 12. What I don't, let's see. So we're not pure single electron eigenstates. Do you mean that the charging energies were too small, or was it something else?
It's the broadening that's too much. In this case, the dot energy broadening is about 100 microvolt. And this is on the same order of the induced gap of the superconductor. And if you take a look at, for example, the charge degree of freedom, you would realize that as long as you're still within the superconducting gap, the dot is never a truly electron excitation or a hole excitation. It's some mixture because of the broadening.
Yeah. Okay. And the broadening came from the fact that these dots were not so well controlled or something.
Yeah, so I don't know the motivation behind using these particular fab processes, but in the end, they opt for dots that do not even look very nice.
Okay. Yeah. All right. Yeah, thanks.
Yeah. So what we have over here, as Ivan was just mentioning, is a lot more similar to what the spin qubit community have been looking at. Namely, you use a large number of gates to define one dot, which is not usually not the case in the past. So we will be looking at this measurement setup. I'll just say that we will be sweeping the left dot gate and the right dot gate and measuring the two currents on the two sides in all the upcoming slides. So the first measurement I want to present you is the highest resolution image we have of cross and derivative reflection to date. So this is done by applying a positive bias on both normal leads. So that corresponds to negative energy. And what we have is if we place the two quantum dots, one above, one below the Fermi energy with equal distance, in this case, our Kuiper pairs will sometimes split into the two quantum dots because this process is energy conserving. It happens at a relatively high frequency. After they split, these two dots can effectively, very efficiently tunnel into leads because the Fermi seas there are empty. And what we see is basically this very strong resonance feature along an anti-diagonal line corresponding to the dot energies having opposite sign but equal amplitude. And what we see is also that the left current and right current this time are really equal. And this is very nice for, of course, all the electron entangler experiments that people want to do in these systems, because now really for the first time, you take a measurement and the majority of the electrons registering as your current really comes from a Cooper pair splitting process instead of either local pair tunneling or co-tunneling. So from this measurement, we can extract.
Sorry, can I ask one question?
Yeah.
Hello. Hi. I want to ask about those figures. So basically, it's showing that when you align those two quantum dots, you got enhanced current. Do I understand correctly? Yeah.
Yeah, exactly.
Okay, I see. Yeah.
Yeah, anti-align in this case. Yeah, just to be precise with language. When the two dots energies.
Oh yeah.
Are
okay,
opposite.
I see. Yeah. Okay.
Yeah. And of course, if you align, this leads me to the next slide. We can also do another kind of measurement. We make the biases on the two normal leads opposite. This one negative, this one positive. And then what we have is what the double dot measurements very often show you. We have a very strong feature along this diagonal line where the two dot energies are equal. And also the current on the left, on the right are exactly the same, meaning that we really have one electron going to the left and coming out via the right again without entering the superconductor. So if you pay closer attention, in fact, you can even see this bias triangle that's very often, you see very typically in double dot measurements. So I have briefly described the charge degree of freedom measurements. And for the remainder of the talk, I'll focus on the spin. And to look at the spin, what we do is actually to expand our measurements to 4 charge degeneracies instead of 1. And if we sweep the left gate and right gate in a larger range, what we do is we fill the left dots from 0, 1, 2 and the right dots 0, 1, 2, one by one. And also at these 4 charge degeneracies, we can remark on 2 things. And at 0 magnetic field, what these different charge occupations differ with each other is the degeneracy. For example, when the right dot has 1 electron, you can imagine there's a twofold degeneracy at 0 field, and this does not apply obviously to the bottom left corner. At finite magnetic field, this will be our charge spin filters, because if once we remove the Kramers degeneracy, we would really fix the spins that each charge degeneracy prefers. And what we have is basically 4 charge spin filtering polarities, and we will later use this to diagnose the spin. But
sorry, we have a question from Giordano.
Yep.
Giordano, if you want to unmute yourself.
I just wrote it in the chat. It's a simple question. So just for people that are not expert in the room, when the superconductor in the middle, you're referring to the actual aluminum coating the nanowire, or the section of the nanowire that is proximitized underneath?
I will come back to this in the last 2 slides, because it's actually the latter. It's the superconducting induced semiconducting states that are mediating these coatings.
Okay, thank you.
Yeah. But for now, let's just imagine it's a superconductor for the sake of not getting to the black box of the middle. Yeah. So what I was trying to alert you to in this sweep is that we have measured across the Andreev currents at these 4 charge degeneracy. You might have noticed that this corner is particularly weak. And the reason for this signal being weak, we understand as the follows. And so at this particular bias setting, we have positive energy on the 2 normal leads, and these normal leads will send electrons into the dots. Because it's 0 field, we have Kramers spin degeneracy. We might be very unfortunate such that our 2 leads decides to send both the same spin onto the dots. In this case, our transport will be entirely blocked because, first of all, what we have is a singlet superconductor at 0 field, and we cannot recombine 2 Cooper pairs, but the electrons can also not really go back to the leads because they're already occupied with by virtue of the bias we apply. So this effect should be very familiar also to the dots people, and because you must have seen this, where our quantum dot currents get very diminished when we are at 0, 1 and 1, 0 charge degeneracies. This is known as Pauli blockade. And what our measurements do is actually to complete these 4 quadrants of Pauli blockade. And because now we can apply, for example, the same bias on the 2 normalies, which for a double dot measurement is really not an option. And in this way, we can use the superconductor to mediate Pauli blockade and observe the whole 4 quadrants, depending on how we apply the bias. And the message of this slide is essentially that what we have here is only possible when both our quantum dots are 1 orbital level, and our 2 degenerate spins are really originating out of 1 orbital. So what we do, when we do sweep the 4 charge degeneracies, we're really diagnosing the spin by without changing the orbital. So finally, we come to what I promised, which is to look at the spin at finite magnetic field using the dot as spin filters. In this case, first of all, I have up to now neglected to tell you that, in fact, the reason we use indium antimonite nanowire is because of the very strong spin orbit in these materials. And the spin orbit in this particular device follows a direction that is perpendicular to the wire, but in the substrate plane. So if we apply a magnetic field in the same direction, we only have 1 spin quantization axis in this whole setup. And then spin is a good quantum number. And because aluminum is eventually S-wave, absent of spin flipping mechanisms, we really have no way of combining 2 equal spin electrons to form a Cooper pair. And that is exactly what you see over here. When we vary the 4 spin combinations, what we do see is that the opposite spins are fine. They can recombine into Cooper pairs, but the parallel spins cannot. And the same perspective, of course, also holds if you look at the elastic Cotant link, and we can remark that the spin is conserved, meaning that spin flipping Cotant link is forbidden. And this changes a lot if we rotate the magnetic field to point 90 degrees parallel to the nanowire, but perpendicular to the spin orbit field. In this case, imagine, let's say the quantum dots are still polarized roughly along this X direction, for example. And if we shoot an electron pointed along X, but the spin orbit field points along Y, we are compelled to go through spin precession. And this makes the injected spin acquire a finite down component, which allows it to recombine with the up on the other side. And as a result, we do see that at these up and down corners, we have a very faint, however, finite signal. And this is really resulting from splitting a Cooper pair into 2 electrons with the same spin. And finally, we can, of course, put everything into, like we can sweep the field in the entire substrate plane, plot everything in 1 sweep. And then what we see is that our spin is only conserved along these 2 special directions, 90 and 270 degrees, corresponding to angles that are parallel to the spin orbit field. And our triplet component really gets the strongest when the field is perpendicular. So I don't have too much time to go into this last part, but I think it's rather crucial. So I will still mention, because up to now, I have indeed neglected what is happening in this central hybrid part. So this is really a half semiconducting, half superconducting structure. And because it's also semiconducting, we can in fact use the gate underneath to gate the energy spectrum inside this segment. And what we see is that if we just plot the cross-Dendreev and elastic Cotant link amplitudes as a function of this particular plunger gate underneath this hybrid segment, we see that both processes go through periodic ups and downs. And the most typical situation is whenever you have a peak of cross-Dendreev reflection or Cooper splitting, it's accompanied by a dip in elastic Cotant link. It's the same here, and then it gets obscured by other features, of course. But then the reason for this behavior will become a lot more obvious if we overlap this with the measurement of the energy spectrum in this central segment. So to do this measurement, we open up all the tunnel barrier gates outside, and we don't have dots anymore. We just have a tunnel barrier. And what we see is a series of Andreev bound states, which naturally occur in confined semiconducting, superconducting hybrid systems. And these Andreev bound states go through energy modulations as a function of the gate. And these cross-Andreev signals precisely become the strongest at the energy minimums of these states. In fact, this is very well modeled by a theory developed by Chen Xiao. here at QRE. And I will only summarize the finding as elastic co-tunneling and cross-dendritic reflection can, in fact, in this system, be unified in one framework, describing both as a second-order virtual hopping through the same middle and derivative bound state. And the finding of this particular mechanism is that we can now use the semiconducting gating capability to continuously tune the cross-dendritic and elastic co-tunneling amplitudes. And this has, of course, very important consequences. Well, to begin with, it gives us a clue as to, for example, because all I've shown you is DC measurements. It's slow measurements. How do we know, in fact, this is a result of Kubernetes splitting and not some random diffusion process that just happens to be caught by your dots? So the clue we have is over here, this dip. This dip is rather peculiar because it is a result of the destructive interference arising out of two possible quantum paths differing by a minus sign. And this minus sign is a result of the fermion exchange statistics. The fact that we can observe this kind of coherent effect gives us a clue that what is happening in these devices is very likely coherent processes instead of just random stochastic diffusion. And this gives us more confidence in, for example, for setting up a Bell test equipment experiment in the future. And then this, of course, has the other consequence that at this particular gating point, our cross-dendritic signal is the strongest. And this is the ideal point for doing such an electron entangler experiment because you only have the desired Kubernetes splitting process and not any competitor. And finally, there's a very peculiar point where elastic co-tunneling and cross-dendritic reflection can be tuned equal. And this will be expanded upon in a lot more detail in the next talk. I see I'm already on time, so I will just show the conclusion. And if there's a quick question, for example.
Yes, there is a quick question in the chat from Xiao. In slide 23, are two currents the same in the figures? I don't know, Xiao, if you want to add anything.
Let me just...
Yeah, in slide 23, where you change the angle of the magnetic field.
Yep.
Yeah, this. Oh, okay. But here you don't. Okay. But I see that there's some oscillation. So, for example, for the lab 2 figures, there is some right for the. Okay, for the up, down, down, and up, up for the most rightmost and leftmost figures, they do not match exactly.
Yeah, exactly.
Right.
So yeah, so we don't really understand what's the exact difference, but I'll just mention that in real life, it's not only the dots that get spin polarized by the field. The Andreev level also gets spin polarized. So the up and down do assume different roles. And this does mean that, for example, the down spin will get closer in energy to the dots, which enhances the co-tunneling magnitude.
Okay. Okay. Thanks.
Juan, thank you very much for your talk. I'm sure if there are more questions, you can directly send an email to Guan. For the sake of time, I will get to you, Tom. So our next talk from Tom Dvir is realizing a minimum Kitaev chain in indium-antimonide hybrid nanowire. Tom Dvir obtained his PhD from the Hebrew University of Jerusalem in 2019, where he studied superconductivity in ultra-thin van der Waals materials. He later joined the group of Leo Kouwenhoven in QuTech to study topological superconductivity in hybrid systems of superconductors and semiconducting nanowires. So as before, please feel free to raise your hand and I will give you the word and you can ask questions to Tom. Tom, the floor is yours. Thanks.
Thanks, Grazia, again for organizing this, and thanks the audience for sticking around. Indeed, in this second part of the talk, I would like to show results coming from exactly the same device as the one Juan showed, but with a slightly different angle, let's say. And to start with, actually, I would like to zoom out quite much and to talk about the goal of, or let's say the goal of QURI. Okay, what do we want to do here? And I think that a lot of efforts in the Qubit research group, or the topological group, as it was called before, states around this magical particle, which we called Majorana, or Majorana-bound state. And there is a reason for this. And for sake of, I think, people of other groups, let's have a quick discussion about that. So Majorana particle was, let's say, hypothesized about 90 years ago by Majorana regarding elementary excitation, elementary particle that is its own antiparticle. This is not the subject of our discussion. What we are going to talk about here is about an emergent particle. So we take a condensed matter system, a superconducting system, and we try to find these exotic states that live within. And they have a few special properties. So the first property, which gives it its name, is that these properties are their own antiparticle. And by virtue of that, it means that they lack a lot of interacting elements with the environment. They don't have charge, they don't have spin, which makes them quite robust to interferences. Another thing that is characteristic of these states is that these are delocalized edge modes. So usually we take a system. In this case, this is our model system that we like is a nanowire, but it doesn't have to be so. And we find these Majoranas located at the edge of the system. And that's nice, because if there is a quantum information that is stored in this system, it is delocalized. And by that, it is unsensitive to disturbances that occur only on one side of the system. And if we can make the system long, that's a pretty good thing to do. It relies on a ground state degeneracy. So the Majorana can be occupied or unoccupied, or if you wish, maybe some underlying many-body structure can be even or odd. So there is a two-level system or two-level nature to this particle, which points out that it might be used at some point as a qubit. And finally, it is non-abelian. And this non-abelianness of these Majoranas means that we can exchange them and exchange them once more, and we get a non-trivial phase. So we can extract or store information in these states. And all of this gives us the motivation, which is to have a low decoherence topological quantum computer. So if we can get these Majoranas and we can use them, that can be nice. So it might save us a lot of energy in achieving a fault-tolerant quantum computer at some point in the future. And there is a lot of effort in looking for them. And one maybe the first effort or first idea of where to look for them is actually not related to superconductor. It relates to fractional quantum Hall states. And it proposed that we can find such non-abelian particles there. And well, they were not discovered quite yet, but at least their anionic or abelian particles were already discovered quite recently, in fact. So that's one option. And they were also proposed to sit on topological insulators. So this is maybe a second proposal by these two guys, Fu and Kane, which led to a lot of research. And the idea was that we take this topological insulator who has a band structure, which is already chiral. And then we attach it to a superconductor and we get Majorana-bound states. And perhaps they showed up. Perhaps, so there are a few candidates. In this example, I show one of them, but there are a few materials that might fulfill this promise. And another quite promising direction, which is not the one we are taking, is what happens if we just take, maybe with an STM or find a different way, and we pattern a few atoms on top of a superconductor. So we take a magnetic atoms and we pattern them on top of a superconductor, and we see what comes up. And when people do that, they find these delocalized zero modes, which look very much like Majoranas. And so there are a few options on where to look for Majoranas. And when we analyze them, what we see is that all of them include, at least those of the superconducting kind, include these three ingredients. So we need superconductivity because we're talking about topological superconductivity. So that's pretty obvious. What is less obvious is that we need a magnetic field. So we have to break Cramer's degeneracy. And the enemy of the Majorana, since it's its own antiparticle, is another Majorana. So in order to have just one copy of our system, we need our system to be completely non-degenerate. And for this, we need to break time reversal symmetry, or we need the magnetic field. Now, these two components is quite difficult to make them go together. And for this, we need a glue. And this glue is spin-orbit coupling. Spin-orbit coupling acts as a source that works on superconductivity. It rotates it a little bit. It brings it a triplet component, as one described in the previous talk, and allows us to actually have some superconductivity in the presence of magnetic field. And this is common to all the Majorana proposals. And taking these three ingredients and pushing it to the limits of simplicity, in 2010 came two seminal papers that predict that nanowires, semiconducting nanowires, indium antimonide or indium arsenide, doesn't really matter, when you couple to superconductor, should be the place where we look from errors. And this was very exciting, because this is, in relative terms, easy. You take your nanowire, which people know how to grow, you attach it to a superconductor, you have to solve a few materials problems, and you have your Majorana. And people here and other places went ahead and did exactly this, and got what looked like the hallmark signature of the Majorana bound state. So look, for example, maybe we can look at this one. It's very clear. So I just collected a random, let's say, copy of pictures that looks like Majoranas. So what we do is we look at the spectrum, we look at the energy. So the y-axis here is an energy of our experiment, our tunneling experiment. And we see that in zero field, so the left part, we have a gap in our superconductor. And then we apply a magnetic field, and we see that suddenly a zero bias peak appears, which is quite stable. And we see it here in the work of Copenhagen, again, work of Copenhagen. And here we see it in the very first report coming from here, and maybe one of the most recent reports also coming from here. We see it over and over again. And this, of course, is very exciting, because you have a prediction and suddenly it comes to be. But there was a problem, and the problem was disorder. So people began to realize, both theoretically and experimentally, that these wires are not as clean as we would like them to be. And they are actually disordered. And the disorder is a double-edged sword. So on the one hand, what it does is it ruins the topological phase and prevents us from actually creating Majorana. But that's not the only trouble. The only trouble is that it actually mimics the signatures of Majoranas. And in fact, it is incredibly difficult to take a look at one of these images and to point to the origin of it. Is it or is it not our desired topological object? So we need a new paradigm, something that will help us mitigate this. And we have that. And the new paradigm is what we call a Kitaev chain. So instead of relying on a clean system, we actually push disorder to its limits and rely on a connection of quantum dots. So the Kitaev model, and this is what I'm going to explain in detail and post theoretically, and we'll show our experimental progress here, is it relies on a series of quantum dots. So we have a few quantum dots, 1, 2, 3, 4, how many you want, and they are coupled by a superconductor that lives between them. And this gives rise to two types of interaction: cross-wave reflection, as one described, when two electrons from two dots enter the superconductor and leave it simultaneously, and elastical tunneling, when an electron hops from one dot to the other. And if we manage to have this in the presence of enough magnetic fields to spin polarize them, we actually reproduce this model, which is called the Kitaev chain, that will give us our desired Majorana bound states. And it's enough. So if you look at such a chain, it's enough actually to have maybe 5 or a bit more of these elements in order to create a truly topological phase transition. And what is even more remarkable, that even if we have only 2 sites, so you can hardly call 2 sites a chain, but even if you have 2 sites, you can have what we call poor men's Majorana, and which is Majorana bound states that are not part of a topological system, but nonetheless show all the properties of a Majorana bound state. So I think last slide of theory, and then we go to experiments. But let's just get to some grips or get some intuition about the Kitaev chain. So let's consider our system. We have a bunch of quantum dots. Each quantum dot has some energy, chemical potential, which I denote with the letter mu. And each such dot is coupled by two terms. One of them is cross and reflection, which is a process in which takes two electrons from the dot and pushes them into the superconductor or the opposite. And by elastical tunneling. We have an Hamiltonian, which looks something like this. In order to have some intuition, what is very nice to do is to do a mathematical trick and reformulate this Hamiltonian in the Majorana picture. Okay, so we separate each site here, each electronic site, into two other sites. And we call these sites Majoranas because they obey the Majorana relationship. But right now, there's nothing special about them. Now, when we look at the Hamiltonian, we see that the chemical potential or the energy of each site actually couples two Majorana operators that sit on the same point, on the same site. So it's completely local. And then there is interaction between adjacent Majorana sites. One of them is coupled with an amplitude, which is the sum of delta cross-term reflection and T elastical tunneling, and the other one with the difference between them. So far, nothing special here, but we can consider a very special point in the phase space. What happens if the chemical potential is 0 and T equal exactly delta? Then we get rid of most of the coupling and we remain with two uncoupled Majorana bound states. That's precisely what we are after. So again, if we manage to magically push the system into the T equal delta or car equal elastical tunneling amplitudes regime, we can get two Majoranas which are completely delocalized. Okay, experiment. So we go back to our nanowire, which one describes very well. It's an indium antimonide nanowire with a short, about an 18 nanometer superconducting segment in the middle, and two quantum dots which sit on both sides of it. We can characterize each quantum dot by itself, and we see a conventional Coulomb diamond structure. We vary the bias that we apply on each dot versus the energy of the gate underneath it, and that's true for both sides. And when we apply magnetic field, we see that the dots spin polarized. So we see that one resonance goes down with energy, which means that it is spin down. The other one goes up in energy, which means that it is spin up. And the same holds for both dots. And the important number here is that the huge G factor of indium antimonide means that with a moderate magnetic field of 100 or even 200 millitesla, we have a lot of Zeeman energy. So the dots are completely spin polarized throughout the experiment. And that's a point to consider. And by the way, I didn't mention that. Please do ask questions if you have to make the talk more interesting. All right. So to see how the dot interacts, what we should look at is a charge stability diagram. So what we are doing is we are taking our system, our two quantum dots, and we apply a little bit of AC conductance or AC amplitude on one side, and we see whether or not currents go through. One option to do it is to well, make the spins of the dots be equal, and then we get a charge stability diagram of this sort. So on the x-axis, we change the chemical potential or the energy of the left dots. On the y-axis, we change the chemical potential of the right dots. And the corners of this charge stability diagram have different occupation. For example, in this corner, the energy of both dots is low, so both dots are unoccupied. In the other corner, both dots are occupied. And in this corner, the right dot is occupied and the left dot is occupied. What we can see is that there is a gradual transition between the right dot being occupied and the left dot being occupied without a dramatic phase transition. This means that in the middle, we form a hybrid. So the ground state in this point is a superposition of an electron sitting on the right dot and the left dot. That's quite standard, and you see it always when you take a bunch of quantum dots and you couple them through tunneling. But what we can do, and in this case, what we're going to do is we're going to change the spin of one of the dots, so not down, down, but now up-down, we see a different charge stability diagram. Here we see a gradual transition between both dots being empty to both dots being occupied. This is a radically different transition because it means that we couple quantum dots through crossed and wave reflection. And this was not seen before, and this was our goal. So just to stop here for a minute and to summarize what we've seen, we have taken two quantum dots which are completely spin polarized, so remove primers that you see, and we can couple both of the quantum dots both by elastic co-tunneling and by cross and wave reflection. These are the ingredients that are required to a Kitaev chain. So in principle, we could have stopped here and imagine that we take this technology, which we know how to do, and multiply it multiple times. Then we would have a Kitaev chain, which would show a topological phase transition. But we can do something more. Since the cross and wave reflection elastic co-tunneling amplitudes are modulated by the gates, we can try to see if we can control them also here. So we apply what we call a plunger gate, or the gate that controls the hybrid nanowire, and we fix it at some value, let's say 220 millivolts, and we see charge stability diagram of this form. So we see that there is a gradual transition between dots being empty to dots being full. So cross and wave reflection is a strong element in this system. And this we see in the local conductance, GLL on the left side, and the local conductance, GRR on the right side, but also in the non-local conductance. So we see that something comes in from one side, what comes from the other, and it shows exactly the same spectrum. Now we can change that gate and see what happens. And what we see is we see the opposite charge stability diagram. What we see is a transition between the odd state. And as a result, we also see that the non-local conductance has changed its sign from being positive to being negative. And if we could gradually tune between having a cross and wave reflection bigger than tunneling to tunneling being bigger than cross and wave reflection, there has to be a point in the middle where they are equal. And indeed, we look for that, and we find a point in which there is no level repulsion, and the non-local conductance shows both a positive and negative correlation. This is the Poormans-Majorana sweet spot, where even with two sites, we could separate our system into two decoupled Majorana bound states. And we can also measure the spectrum continuously, and we see that if we start with a gap when the chemical potential is zero, with some value of the plunger gate, we can quickly close this gap and reopen it, and by doing so change the interaction from being cross and wave reflection dominated to elastic co-tunneling dominated. I'll spend maybe 3 more minutes in looking closely at this Poormans-Majorana point, because it's actually our goal to talk about the Majorana bound states. So we can go back to theory for a minute. If we manage to have this special Poormans-Majorana point, there are indications for it. The signature of a Majorana bound state is a zero bias conductance peak. And this zero bias conductance peak, so if you look at the theoretical spectrum, is this line here in the middle. So you see that it happens at zero energy. And what is special about it is that if we change the chemical potential of one dot or the other dot, this zero bias peak is robust. Okay? And maybe I'll open parentheses and say that even though it seems split here, in fact, this splitting is a different effect. In principle, the zero bias peak is robust when we change the chemical potential of one dot. But when we change the chemical potential of both dots, so we have a non-local interaction with the system, the zero bias peak splits. So this is something we would like to see in the experiment. So we go to our charge stability diagram and we measure it. So we begin in the center and we have a nice zero bias peak measured both on the left side and on the right side. And by looking at the spectrum, we can also extract some numbers. So we see that the interaction is 12 microvolts, which is maybe a bit small, but still large enough to be seen. Now we change the chemical potential of one of the dots, and we see that the zero bias peak persists, just as we want it. We change the chemical potential of the other dot, and the zero bias peak, while being small, persists, just as we want it. Now we change the chemical potential of both dots, and we see a gapped system. So the zero bias peak on Majorana is completely gone. Putting it all together, we can see the continuous evolution. For example, when we sweep along one axis, so we change the chemical potential of one dot, we see that, my pointer, we see that the zero bias peak persists on both sides of the device in agreement with the theoretical modeling. Similarly, when we sweep along the other axis, we see that the zero bias persists on both sides of the device in agreement with theoretical modeling. And when we sweep along the diagonal, so change the energy of both dots, we see that the zero bias peak splits, again in agreement with the theoretical modeling. With this, I would like to conclude. So just to remind you what we have seen, we could reproduce in the experiment this very, very simple model in which two spin polarized dots are coupled simultaneously by cross-ray reflection and elastic co-tunneling. By controlling the plunger gate in the middle, we can systematically tune our system between being dominant by elastic co-tunneling or be dominant by cross-ray reflection and fixing the system in a sweet spot in the middle, showing Majorana bound state. And what is most important is that this is just the beginning, because with the same technology, we can extend it to have a much more robust Majoranas in a long Kitaev chain on the one hand, and in the other hand, we can already take what we have and study the very, very exciting amount of experimental proposals that are situated around the usage of Majorana bound states on a billion, the nonabellion of this state. Yeah, and that's the end of the talk, and I will be happy to answer questions if any exists.
Thank you, Tom. So let's see if there are any questions. You can just unmute yourself.
Maybe I can start. Yeah, thanks, Tom. Very nice, and Guan. So if there weren't, yeah, I mean, I could follow it, but not in full detail. So maybe my question is a stupid question, but if you look at the plots shown here, right, and there is only elastic co-tunneling and no cross-Andreev reflection also in the picture, what would those plots look like?
Okay, yeah, so in these plots, you cannot distinguish, you actually see the difference between elastic co-tunneling and cross-Andreev reflection. Okay, so here, for example, you see that T is bigger than delta, and the distance between these 2 points is T minus delta, and oppositely here, it's delta is bigger than T, and you see delta minus T. So at least in these two extreme plots, you will not be able to tell that you have simultaneous chronicity, only one of them. That's of course not true for the middle one. For the middle one, you need both. Otherwise, you will not have the avoided crossing. We have other ways to detect that actually, even in these plots, we have both elements. And the way to do it is to look at the difference between local and non-local spectroscopy. For example, if you have only one.
So sorry to interrupt, but can I still ask further on what you just said? Right. So if I look at the middle plot,
yeah,
is that not a plot that you could also get if there were only elastic co-tunneling?
No, so you could in principle get such a plot if there would be no interaction at all, and then there is no avoided crossing.
Yeah, I mean basically if there's still inelastic or elastic co-tunneling, but then simply with small small enough coupling so that the avoided crossing is not visible.
Yeah, you could, but then you'll have a very, very small amount of transport. So we can model it, and we see what we get. But furthermore, we actually see a continuity. So we see that we go from one to the other by a continuous transition. And we can measure them. And specifically for this point, what you would see if you had only very little amount of one of these processes, you will not get these two side peak at this specific value. So what you're seeing here is only the zero bias part. But looking at the full spectrum is actually quite telling. So see precisely how it behaves. And this is in fact shows us the numbers.
I think maybe there's 2 points to this question. One is that we can also simply go back to the measurements I was presenting, namely just singling out cross-Dvir and ECT and measuring them separately. If you can detect both, it just simply means both are present, and that's the case. And the second fact is actually, imagine if your cross-Dvir and elastic tunneling coupling both go to 0. In fact, what you're left with is you're trying to shoot electrons from a normal lead through a dot to a superconductor. And because we don't have local Dvir, as we established from the beginning, this will simply not work because you're not allowed to shoot single electrons into the superconductor. So our expected observation when we have only one kind of coupling and that one dies to 0 is actually you would simply cease to have any conductance at all. So this is how we ensure. Indeed, this is a question we also wondered ourselves, and we had to check that.
But then returning to Giordano's question of before, that argument only holds if there is really induced superconductivity in that semiconductor, right? Otherwise, there wouldn't be a problem of having single electrons going into that region.
Yeah, but so maybe it's good to look at. So I show here a zoomed in version, but when we zoom out, you actually see that with one dot you have 0 interaction, you have 0 current. So the gap is hard. And you can see hints for this, right? Because you see that the current decays very strongly. And if you zoom out more, you would see that it decays completely.
Yeah. Thank you.
I have one question. In one of your slides, when you show the Hamiltonian, one of the conditions you mentioned to have this Majorana 0 mole, one of the conditions is to have 0 charging energy. Is that the case here? Am I missing something?
Yeah, so the charging energy on the dot is actually very important in order to kill any local process. But what we have is 0, let's say, chemical potential. What it means actually that we place the dots in the charge density point. So we place the dot, we just apply just enough voltage, so the dot doesn't mind if it has 1 electron or 0 electrons. So we balance out the charging energy which exists with a gate. Now, you can of course consider what happens if you have an additional charging energy, for example, on the superconductor, but that will change the picture. So the superconductor does not, at least in this model, does not have charging energy, but the dots do. Was that your question? Okay, so here when you say the charging energy is 0, that's in your experiment, that means you align your dot level to the normal lead. Well, right. So
the charging energy is absorbed into the mu. So if you just don't count all the occupation numbers, if you only restrict your view to a low energy subspace of the Hamiltonian near a charge degeneracy, you can just absorb everything into this linear mu.
Okay. I'll think about it. I'm not sure if I understand. Okay, but thanks.
I'll be happy to explain more if you wish at some later point.
Okay, well, I want to thank you very much, Guan and Tom, for your talks and for being here. I would like to end with a round of applause. So please unmute yourself and give Tom and Guan a great applause.
All right, thank you very much.
Thank you, everyone, for being here. And I will see you at the next QuTech360 seminar. Have a nice evening. Bye.